Hello students, I welcome you for another tutorial of software engineering. This is our second topic to discuss, and today we are going to look at software processes. By names of Lubinga Hudson from Uganda. Don't forget to subscribe to my channel, and please invite your fellow students also to learn and to watch these videos. We had the first video, you can look for it in case you didn't watch it, and this is our second tutorial. So in this tutorial we are going to look at software process models, process activities, coping with change, the rational unified process, and in that we shall look at an example of a modern software process. So let's begin with understanding what a software process is. Now, a software process can be defined as a structured set of activities required to develop a software system. So when you are developing a system, remember, whenever you talk about a system, it's a combination of several components. So when you are developing a software system, we have a certain process that we follow. And this process, anything called a process, is also a combination of several activities that have a structured nature. They have a certain flow. So that is the process that we are going to look at. In case you want to develop a software, what processes do you undergo to come up with a good software system? Now we are saying that many different software processes may involve these. One, specification, and here you are trying to understand, to know, to decide what the system should do. Then another one is designing and implementation. Under this, we are defining the organization of the system and implementing the system. So here you come up with certain designs, as in diagrams like UML, like use case diagrams, like class diagrams, and so on. And these diagrams will be defining how the several components in the system are organized and how they interrelate. And after that, you do the coding, that is the implementation, when you are looking at the design and now making that design to become a system. So we do that by writing a software program, or what we normally call coding. Then under that, under the software process, we also have validation. Validation simply means checking to see if the system does what exactly the customer wants. Validation is different from testing. Testing, on the other hand, is it involves checking to see that the system has no failure. In other words, it is free from error and bugs. But validation, you are trying to check if the system is doing what the customer wants. Then you have evolution. Here, if the system in the future has some changes, okay, these changes are due to the users. They may get other requirements, and you have to provide a way of adding those customer needs. So that's what we mean by a system evolving, when it is changing due to the changing customer needs. So a software process model is a model that we follow. There are several models that we are going to look at, and these models, or any model, is an abstract representation of a process. So a model is a process. In brief, it tries to help you follow a certain flow of steps, and there are several activities. So there are several models that guide us, and it depends on the type of software and what the software engineers want to choose a suitable model for the software system. So this model presents a description of a process from some particular perspective. Now let's talk about plan-driven and agile processes. Plan-driven, as the name indicates, these kind of processes depend on a certain plan that is already set or created. So these processes have activities that are already planned in advance, and now to ensure that you are progressing well or you are faring well with the system, you have to measure against this already existing plan. On the other hand, we have agile processes. Under this, the planning is done incrementally. You keep on increasing or you keep on adding changes to the processes. So this is in this kind of processing, it is easier to change the process. So if there are emerging customer requirements or needs, it's very easy to incorporate them because it is incremental. You keep on increasing the scope as you add functionalities or requirements to your software. So in practice, we are saying that most of the processes and the models that you are going to look at may include both of these approaches, the plan-driven approach and the agile approach. So in practical, these two work hand in hand, and there is no right or wrong software process as long as you have a reason as to why you are choosing that process. So this takes us to the software process models. These are the 3 general software process models. We have the waterfall model, incremental development model, reuse-oriented software engineering. Now in waterfall, it is a plan-driven model, so it takes the plan-driven approach. That means you have to plan everything before you start the software project. So this waterfall model separates the phases of the software development, and these phases are distinct. They don't interrelate. You have to first finish the first phase before you continue to the next phase. What about incremental? Incremental is based also on the plan-driven or agile. It can be both, depending. But with incremental development, you do the specification, the development, and the validation. But as you are doing these processes, you can go back and then add and come back. For example, you can specify a few changes you started developing. As you are developing the software or coding, you get other requirements. Now you get to know that this system also needs to do this and this. Then you still add it in the development. Then you can validate a module that is working to see that it's working well for the customer. And again, you go back and develop another module. So they are interleaved. So it may be plan-driven, it can be agile when you are adding, or plan-driven when you first plan everything and then you start the development. Then you have reuse-oriented software engineering. For this process model, the system is assembled from existing components. It can also be plan-driven or agile. So you get already existing components. They may be from several other software products, and now you build a system from already those existing components. So that's what we call reuse-oriented. So you are using the already existing components again. That's what you mean by reuse. So we are saying in practice, most of the large systems are developed using the processes that incorporate elements from all these 3 models. So let's talk about the waterfall model. This is a diagram showing trying to show the waterfall model. So in the waterfall model, we begin with gathering the requirements and we define them. What does the user want? What do they have in mind? So you can gather requirements using interviews. At times you can observe. You can use focus groups. You combine users into groups and ask them questions. Then you get to know what they want and the reason as to why they want the system. Then you have system and software design. So after gathering the requirements, you come up with a system design or the software design. You try to draw diagrams to show how the system will flow and how the different components will interrelate. After that, you go to implementation and unit testing. Implementation, that's where you do the coding or the programming, and then unit testing. Each unit that you finish, you test it as a unit to see that it's working. Then after that, you go to integration and system testing. So each unit that you have tested here and is working in this phase, you integrate, that is, you merge them or you combine them to see if the different units can be combined and work together. And if they work together, then you test them as a whole system, because the system is the combination of these several units. Then after that, you go to operation and maintenance. Operation is when you put the system into use, so the users will start using the system when you deploy it, when you install it, and the users are using it. But now the maintenance stage will continue. You ensure that the system continues to work properly and it continues to work as expected. That's maintenance. So this is the waterfall model, and these are the different phases that you go through. So I've explained them. I may not waste a lot of time in the following slides. But one thing you should note with the waterfall model, as the name indicates, waterfall. You ask yourself, can water flow back if water is falling? Take a look of water flowing in a stream or the rainwater. Can it fall and it goes back? No, it can't be. So when you finish this phase, you continue to another phase, and you have to finish everything here before you continue, and so on. So that's the waterfall model. So we have seen these separate phases in the waterfall model, but we are saying the main drawback or the disadvantage of the waterfall model is the difficulty of accommodating change after the process is underway. So in case there is a change that you want to put and you have already finished the process, since if you are following the principle of this model, you don't go back. That means you have no option. Maybe you can just leave it. So that's the main drawback. So in principle, you're saying a phase has to be complete before moving on to the next phase. That's the principle of the waterfall model. So let's talk about the problems in the waterfall model. Inflexible partitioning of the project into distinct stages makes it difficult to respond to changing customer requirements. So in case, as you are still doing, customers, I've already told you that, I think in the first class, that customers in most cases don't know what they want. So as you are coming up with a design, they will bring in other new requirements that you need to incorporate. Now with the waterfall model, you can go back. That means it's inapplicable in some cases. So therefore, this model is only appropriate only and only when the requirements are well understood, meaning there won't be changes or maybe very limited changes during the design process. So due to this, few business systems have adopted this model because few of them have stable requirements anyway. These businesses, most of them have changing requirements. Now this model is mostly used for large systems engineering projects. For these large systems, you can work in each phase can be on a different site, and all the requirements have to be well understood, and you only work on your module or your phase. So in such circumstances, this waterfall model is of the plan-driven nature. Okay, we have another model. Now, due to the drawbacks of the waterfall model, engineers, software engineers had to come up with maybe another model which can be suitable where the waterfall model may not. So this is the incremental development model. So as the name indicates, you develop incrementally, you add increments, and each increment in this case, whichever increment that you add must have an or must yield to an added functionality. Those are the increments. The increments are more of versions. Yeah, each version you release, it's an increment that there are some things that you have added, and each version at least will yield to some more functionalities in the system. So in this diagram, we begin by outlining the description. The description in general of the system, so you have the requirements and so on. You may not have all of them, but at least you have to begin with the requirements that you've understood well, however much you may not first look at all of them, but the ones that you are going to work with, you must ensure that you've understood them well. Then after that, we have concurrent activities in this. Here, you do the requirement specification, where you determine or you decide which requirements are really important or needed, or you should first deal with. As you specify, you can start on the development, but as you develop, you are seeing these arrows, you can go back and specify other requirements. Then as you develop, you can test those units or the modules that have been finished, and as you test, you can still go back and develop more, or you can be validating at the same time when another person is still developing. And after that, on this phase of specification, it is the initial version of the software, and you can release the version, and you can also go back after releasing it and specify. Still, after the initial version, you can develop intermediate versions or other versions that come in. Now this model is very common. I've also used it in many ways. You go to the requirements, for example, a loan management system, you first only deal with registration of members. You give the initial version. Then you have other intermediate versions. For example, you can add the savings and then the withdrawals. That's another module. And you are seeing that each module that you add gives an added functionality. So you release other intermediate versions until you come to the final version, which has everything, which has cash vault, which has loans, and so on. So that's incremental development. So meaning, because each increment is a version that has functionality, whichever requirements that you begin with, you have to ensure that you have understood them well. So with the incremental development, there are several benefits. The cost of accommodating changing customer requirements is reduced. So since you've already catered for this, adding what the customer wants, if the customer changes the requirements or if it adds more requirements, you reduce the cost, other than the waterfall model whereby you have to do everything afresh. Now it is easier also, this is another benefit, to get customer feedback on the development work that has been done. Wow, this is very, very important. Whichever module release, the customer will be using it. If the customer finds anything that's not okay in a certain version, then you have a chance of releasing another version with the modification. So that's another benefit. Then the third one, we are saying that you have more rapid delivery. So you can deliver software in so short a time, because when you finish a module, you can call it version 1 and release it. They start using it as you develop. So you can deliver in so short a time, unlike the waterfall model whereby you have to finish everything. Then, much as the incremental development model has benefits, it also suffers from some problems. The process is not visible. Now, most of the managers in an organization want visible processes. You may give regular deliverables, but it's not easy to measure those deliverables because these versions had only a few functionalities. That's why there are many versions, like for example Microsoft Word 2015, 2013, 2012. You may not even see the difference, but each version that they release, there must be an added functionality. So it's not easy to measure the progress. The manager may even think that you have just brought back the same version and you've not added anything. So if systems are developed quickly, it's not cost effective to produce documents that reflect every version. Now this is also another problem. For whichever version, you must reflect or produce the documentations for each version. So if you are to release many, it's also not easy. Then another problem, we are saying the system structure tends to degrade as new increments are added. So you may end up with a confusing structure. If you are not steady enough, you may entirely come up with a different software that you had in the start, because you may corrupt the structure and the initial structure of the system. And incorporating further changes every time and then is also not very easy, and it's difficult, and of course you have to pay the programmers, or if you're a programmer you have to ask for more money, so it is costly. Now let's talk about the reuse oriented software engineering model. This one, as I already noted, it's based on already existing components of the system. Now your work is to ensure that you integrate those components. These are components from what we call commercial off-the-shelf systems, COTS. These systems are available online as they are. You just purchase them and use them as they are, because they are not customized. You just use them. They are more of generic systems. Now, if you can use those components from such systems and integrate them and come up with a system, that means you are reusing the already existing components to ease your work. So this kind of model is called reuse-oriented software engineering. And this involves these stages. You have to analyze the components to see if they really work for you. So you must do the analysis. After looking for the components, you have to analyze them and see if they are working, or they are suitable, or their architecture can be combined. Then you have to do the requirements modification. You have to modify the requirements to see that they suit or they are workable. Then system design with reuse. So here you design the system but with the reuse structure. Then development and integration, you code and bring together the components to come up with a system. So reuse is now the standard approach for building many types of business systems. That's the diagram. You specify the requirements, not the specifications. After that, you analyze the components that you have gathered, and you analyze them as you test them, or you look at them against the specific requirements to see if these components will work for you. Then you modify the requirements depending on now the components that you have obtained. Then you design, and with design you have to have a design which involves reuse. Whichever component you have, you can use it again. And after that, you do development and integration. After the design, you develop, then you integrate the components, and you check if the components are working as per the user requirements. That's validation. And then you deploy the system, or you put it into use. Let's talk about the process activities. Now, real software processes are interleaved sequences. They collaborate. These processes are not separate. They are not distinct. Meaning, you can be doing one process at the same time when you are also doing another process or phase. And one person may be doing one phase as another person is occupied with another task or in another phase. So these processes collaborate, and these activities, their main goal, their overall goal is to come up with specific requirements, come up with a good design, you implement and then test the software system as a whole. So the 4 basic process activities include specification, development, validation, and evolution, and I've already explained them. These are organized in different ways depending on the development process or depending on the model that you are using. So for the waterfall, as we noted, they are organized sequentially. You finish one, you go to another phase, and so on and so on. Whereas in incremental, they are interleaved in that you can be doing one sequence. Maybe you can be doing system specification at the same time when you are developing. As you are developing, you can be validating some modules. As you are validating, you can deploy the system into use, and the system starts to evolve there, and then when you have not even finished, releasing other versions. Okay, let's talk about software specification. This is the process whereby the software engineer will establish which services he requires and the limits or the constraints on the system's operation and development. So Under software specification, we do what we call requirements engineering process. So this is the process. You know, when you talk about engineering is like manufacturing, and engineering is a process. So these are, if you are to do software specification, this is what you go through. First, you do what we call the feasibility study. Feasibility study, you try to make some research, that is, you do a thorough study. And here, first of all, you are trying to understand if really the system is worthy. Is it possible technically? Do you have the expertise to do the system? Because a user can tell you to, for example, if you are told to create a system, maybe that will change an animal into a human being. Technically, that's impossible. So, feasibility study will look into all that, and the financial constraints, according to what the user is willing to pay you. Is that money enough? So, is it worthy to undertake the project? That's what is involved in feasibility study. We have requirements elicitation and analysis. That's number 2. Here, when you gather requirements from the user, that's elicitation. You list them, you write them down. You can write using paper as you interview. You talk to the stakeholders, the bosses, those, my project, maybe if it's a company, the managers, then the users who will be using it, even the directors. Now you gather requirements from them, you get their different views and what they want. You can even visit each module or department to gather several requirements, because each department knows their respective requirements better. Now, after doing that, then you have to do the analysis. Analysis, not everything that you gather from them will be part of the system, because some of what they want is not even part of what the system will do. Some of what they want is their processes that they do manually, like to maybe organize files, then you open and note. And some requirements may not be feasible, so you analyze. Now, after doing the analysis and so on, you come to the third process of requirement specification. So here you try to define the requirements in detail and specify exactly what you are going to do in each requirement, and leave out those requirements that won't be achieved. Then lastly, you do what we call requirements validation. Checking the validity of the requirements. You check to see if these requirements really meet, after knowing them in detail, meet the user needs. Are they going to help you come up with a system that does exactly what the user wants? So that's requirements validation. So all these 1, 2, 3, 4 processes combined form what we call the software specification. We have requirements engineering process. So it's the process that you've been talking about now. This is just the diagram. The feasibility study, I've talked about it. After that, you do the requirements elicitation analysis. Then you do the requirement specification. And when you do the requirements elicitation and analysis, you have what we call system models. So you can choose the suitable system model that you will take after looking at the requirements, because the requirements, according to the nature of the system, when you do the analysis, now here you can choose whether you are using waterfall model, whether you're using incremental, reuse-based, and other models like prototyping or spiral that we shall look at. And on the feasibility study, you come up with what we call the feasibility report. Then after the requirements specification, you can come up with user and system requirements. So these requirements can be specified, further grouped into 2 user requirements: what the user will be doing with the system, what the user is expected the system to do, and then the system requirements, even if the user is not using it. There are some requirements the system needs, like if the system will it need internet, that's a requirement. which kind of platform or machine will it run, how many programmers are you going to use to come up with the system, and so on. So all that you come up with a documentation. Even this is a documentation of the model, and this is documentation of the user and system requirements. Now, after specifying the requirements, you validate the requirements as we did, and here from all of these two documents, system models and the user and system requirements, you write what you call the requirements document. So the requirements document will involve now is a combination of all those. Okay, so that's the requirements engineering process. We have software design and implementation. The process of converting the system specification into an executable system. So that's what we call design and implementation. You have the requirements, they are there. Come up with the design of the system. This is normally diagram, different diagrams. Up from, when you look at the diagrams, you can easily now do the coding, because the diagrams will be showing you the flow of the system. So when you do the coding and you do the system, everything, you come up with a system which is executable, or which can be used, which can run on a computer. So under software design and implementation, we can look at each. Software design. Here you design the software structure, and this structure is based on the specifications, the details of the requirements that you came up with. It should realize the specifications. Then implementation, you are now translating the structure, the design, into an executable program, into a program that will be used, that is running. So the activities of design and implementation are closely related, and at times may be interleaved, or maybe they work hand in hand. So this is the general model of the design process. You have platform. Okay, you have design inputs. These are the ones. These are the activities in the design. So the design inputs, you must look at the platform information, the requirement specification, and the data description. Then the activities, you come up with several. You can do the database design, the interface design, component design, and architecture design, and all these three have to work together. So your design should have a correlation in each. Then these are the outputs. From the activities that you do, you come up with the system architecture, the database of the system, how the interface will look like, and the components. So we've already talked about these design activities. Let's talk about software validation. V and V. Validation and verification. I've already explained this. When you talk about validation, we are trying to see if the system is meeting the requirements of the customer. Is the system doing the right thing? That's the question that we have in mind when we are doing validation. Testing, we are trying to see if the system is doing the things well. Is it doing the functionalities in the right way? Doesn't it bring errors? Doesn't it have bugs? Does it respond? Does it do what you expect? So that is testing. So these are the stages of testing. We have component, system, and acceptance testing. So you have component testing as one, or at times we call it development testing. Here you are testing each component individually, independently, and you check if those the component is working well. Then after that, you have to bring these components, you combine them to work as a group. So now you test them as a system, as a whole. Then after that, when still you go to the user will be using the system, and you do the acceptance testing. When your system passes the acceptance testing, that means the user will accept and will use it. So the user will try to check to see if the system is doing what he needs. So these are the phases in a plan-driven software process. These are the testing phases. We have requirement specification, system design, and then the detailed design. And on each, you have to come up with a documentation or a plan that you follow, acceptance test plan. From these two, requirement specification and system specification, you come up with that plan. Then system integration test plan from the system specification and the system design, and then the detailed design, that is the subsystem integration test plan, is the one that you yield from these two. Then you have service. Okay, from here you go to the module and unit code and test. I'm not going to explain in detail. I've already talked about them. Then subsystem integration test, then system integration test. Now this is the whole system test as a whole. Then the acceptance test, and then finally, if the test is passed, the service of the system will be accepted wholly, and the users will start using. Software evolution. Now, software is a product which is flexible, meaning it can change. As the world continues to change, the circumstances under which people work may change, the organization may grow, and new functionalities may start to arise. So as a software developer, you must be able to incorporate the changes. So if the user has more modules that he or she requires, you must also be able to add them in your system. And that is what we call software evolution. So the system will evolve. So this is the process of system evolution. You define the requirements that have come up, the new requirements. Then you assess the existing systems. So you look at the existing system and see if these requirements can be incorporated, or to see whether the requirements that they are talking about are really missing. So you can come up with a documentation showing the existing systems. Then propose the changes. After that, you modify the system, that is, you start to incorporate the new changes. But as you are doing that, still you can go back and the new requirements may come. Still you go through everything and you modify. Then after that, if everything is done, you will come up with a new system that is working, and then you go back to this, assess existing systems. So again, you try to see now the new system, compare it with the existing one, and now you have one new existing system, and now you also document everything. These are the key points so far that we can note. Software processes are the activities involved in producing the software system. We have talked about that. And the general process models describe the organization of the software process. And these models, we talked about them: waterfall, incremental, reuse-oriented development. You read about those other key points. Okay. Now, let's talk about coping up with change. Coping up with change, it's like managing change. When change arises, what do you do? We are saying that change is inevitable. You can't do away with change. One person said that if you cannot change, then change will change you. So even in software projects, we have changes that may come. They are due to business changes. That means even the system has to change to continue being relevant to the business. They can be due to new technologies, and you may need to improve maybe the efficiency of the system, and you may implement it on other platforms or using the new technologies. The changes may also be due to changing platforms that require the application changes. A person may change from Windows and goes to Linux, and you have to ensure that your system now will have to run also on Linux. So the platforms have changed. That means even the software project, if it was designed to work on only Windows, then you have to change and ensure that it can also run on Linux. So if change comes, how do you manage it? How do you handle? How do you cope with change? So since change is inevitable, change leads to rework, to work again. So the costs of change include both rework as well as the cost of implementing the new functionality. And rework, we are saying it is analyzing again the requirements, reanalyzing. So how do you reduce the costs of rework? You can either do change avoidance or change tolerance. Change avoidance here, the software process includes activities that can anticipate possible changes before significant rework is required. So here you can avoid the change even if the user has not told you some of the requirements. You can anticipate and get to know that according to the way I'm seeing this business or this company, they might need this and this soon or in the future, and you just put it there. So that's why when you are doing the evolution, you have to analyze the existing systems. You have to check your system, see if what they want you to add is not there. At times users may have the functionalities and they don't just know how to use them. So to do the change avoidance, you can anticipate the features and you put them there. You can create a prototype system and show them to the customers. You create a system prototype, it's like a sample. You show them to the customers to see if they will need such changes, and then you put them there, so you avoid that. Then another way to reduce the costs of rework, to reanalyze the system, everything, to reduce that cost, you can do what we call change tolerance. Now here, in this process, the changes can be accommodated at relatively a low cost. How? This can be done when you have adopted the incremental development model. So the proposed changes may be implemented as increments, as new versions. Instead of, if you use the waterfall model, then you have to repeat everything. So if you adopt the incremental development model, then you can tolerate the changes. So if this is impossible, then you may have to do everything again. Now let's talk about software prototyping. A prototype is an initial version of a system. As I said, it's just like a sample, and we use it to demonstrate concepts, to try to show the user, to try out some options, and you demonstrate to them. So that's a prototype. So a prototype can be used in one when you are in requirements engineering to help with the requirements station and validation. So you can give a prototype as you want to gather requirements. They will tell you, we don't need this, we like this. It should be like this, it should be not like that. So when you give them a prototype, you demonstrate, then they can tell you what they want and you use it to gather the requirements. You can also use it in the design process to explore options and develop a user interface design. So you can come up with the interface design of the system. You demonstrate as a prototype, as a sample to the users. Then they'll tell you, we want the buttons to be here. We don't like that color. We want a banner to be of this size. These words are too small, and so on. So you get the better user interface when you give them the prototype. And thirdly, it is also used in testing process to run back-to-back tests. So you can use a prototype to test everything, and when you see that it works on the prototype, then you can now implement it on a larger scale. So that's software prototyping. These are the benefits of prototyping. improved system usability, because you have given them the prototype. Like for the design, they will show you what they want, so they will easily use the system because the design is actually from them. Then a closer match to users' real needs, because you are using it to gather the requirements. Chances are that you will come up with a system which will be closer to their real needs. Then improved design quality, so the design will be of good quality. No one will blame you for a poor design because it's the design that they've come up with. Improved maintainability, then reduced development effort. Instead of doing things and you do them again when they tell you that this is wrong, it shouldn't be like that. You just use a prototype and you reduce that effort. We have the process of prototype development. So to come up with the prototype, these are the processes that you go through. You establish the objectives of the prototype. What do you want the prototype to do? Is it for a design? Is it for gathering requirements? Is it for testing? And so on. Then you define the prototype functionality. What is the prototype going to be doing? What features or functionalities will it give out? Then you now develop the prototype. Then you evaluate. You see if it is working as per the objectives. So to establish the prototype objectives, you come up with what you call the prototype plan. Here you come up with the outline definition. Here you come up with the executable prototype. These are the outputs now for each step. And then you come up with the evaluation report. Prototype development. Now, to develop the prototype, you can use certain tools and languages. So prototypes have certain tools and program languages that you may choose. And the prototype should involve leaving out some functionality. One, the prototype should focus on areas of the product that are not well understood. Understand this well. When you are coming up with a prototype, focus on the areas that you don't understand well. Because when you give the prototype now, you give your understanding, so the users will help you to tell you what they want, so you now understand them well as per what the user wants. Then, error checking and recovery may not be included in the prototype, so you may not put a lot of effort on checking errors because it's just a prototype. Then you are saying, focus on functional rather than non-functional requirements such as reliability and security. So don't focus on the security of the system and the reliability, maybe even if it has errors, but focus on the functional requirements. What should the system do? If I give the prototype, how can it help me to further understand what the user wants? So that's what you focus onto. You have what you call 3 throw-away prototypes. In fact, most of the prototypes are throw-away prototypes. When you finish using the prototype, you should discard it after development because it's just a good basis for the production of the system, but it's not the final system. So you discard it. In other words, you throw it away. We are saying it may be impossible to tune the system to meet the non-functional requirements. So some people want to use the prototypes to panel beat, to fix, and then may change them to be the real system. It may yield you a lot of errors, and it may not be something very easy. So that's why we are saying they are to throw away. Then you just use them as the basis for the production of the system, because at times you may not need a non-functional requirements like security and reliability. You may not meet them with if you want to just change the prototype to become the real system. And we are saying prototypes are normally undocumented, so that's why they are not to spend a lot of time on. The prototype structure is usually degraded through rapid change, and the prototype probably will not meet normal organizational quality standards, so that's why they are throwaway prototypes. We have incremental delivery. Rather than deliver the system as a single delivery, we can break the system delivery in 2 increments, and each increment will deliver part of the required functionality. That's very, very important. When you are doing incremental delivery, whichever deliverable or whichever release or version that you release, it should be doing part of the whole functionality that's required. And we are saying user requirements are prioritized, and the highest priority requirements are included in our increments. So when you are using incremental delivery, first focus on those requirements or the functionalities that the users need most. Understand them well. First come up with a deliverable or a delivery or a release that meets those requirements. And once the development of an increment is started, the requirements are frozen through requirements for later increments can continue to evolve. So when you start the development of an increment or a version, we are saying the requirements are frozen through requirements, though requirements for later increments can continue to evolve. You make sure that you understand the requirements well. Now you stop bringing in new requirements, focus on those ones. That's why you're saying that you freeze them. But requirements for future use can keep on coming. But requirements that you have agreed upon to now add to the system, you stop on what you've understood from them and you implement them. Now, incremental development and delivery. Incremental development, I've already talked about this. You develop the system in increments, and each increment has to be evaluated first before you continue to the development of another increment. And we normally use the agile methods, whereby the processes can be interleaved. Then you do the evaluation. The customer can do that, or the user can evaluate to check if the increment is okay. Then the delivery, we have just talked about it. So this diagram is trying to show us the incremental delivery. Define outline requirements, assign requirements to increments in design system architecture, develop system. It's just showing us the flow. We can continue. The advantages, we have discussed them somehow. You can read. Then the problems. Can also read them, but maybe I can throw some light on them. We are saying most systems require a set of basic facilities that are used by different parts of the system. What does this mean? If you have requirements and they are not defined in detail, you may fail to come up with a working increment. It can be hard to know the common facilities that are needed by all increments. Remember, for incremental model, you begin developing, or you begin engineering the product when you at least know some requirements well. But we are saying there are some systems whereby almost each modules will need basic facilities, because with incremental, after developing, you have to provide a way of adding other increments and other functionalities. Now, if you don't start with a good architecture, and to know the right architecture, you must have some knowledge of the basic facilities or requirements for each part of the system, so that the architecture that you are using will incorporate or will work with or will be compatible with all parts of the system. Now, if you cannot, it's not easy to identify those common facilities, so you may end up coming up with a system which in the future may be difficult to add new modules. The next one, we are saying the essence of iterative processes is that the specification is developed in conjunction with the software. And we are saying, however, this conflicts with the procurement model of many organizations, where the complete system specification is part of the system development contract. Now here you also have problems with the procurement departments. These iterative processes, the processes that you go back, that's to iterate, you go back, you add the increment, then you repeat the same processes, you add the specifications, you continue going through the same processes. We are saying it is in conflict with the procurement model. What do we mean? Many organizations, they consider the system specification to be part of the system development, and now you will be going back asking the specifications to understand them better then as you keep on developing. So in the end you may ask for more money which they think you are not liable to, or you don't deserve, because you keep on delivering increments. As you do the specification, you get to understand what they want and you create more increments. Okay, let's talk about the Boehm's spiral model. Now the spiral model, we look at the process being represented as a spiral. A spiral, it is like a cycle, something that goes back, iterative, rather than as a sequence of distinct activities. So here we have backtracking. You can go back in each phase and add other functionalities, and you depend on what you have already done to add on it. So that is the spiral model. Now we are saying no fixed phases such as specification or design. Loops in the spiral are chosen depending on what is required. So we have no phases that are fixed like specification or design. Each loop, it depends on what you require, and the risks are explicitly assessed and resolved throughout the process. So we have because the spiral will be in form of quadrants, we have a whole quadrant which talks about risk analysis. So this is the diagram for the spiral model. I don't know if you can see this well, but these are the four quadrants: 1, 2, 3, and 4. You determine the objectives, alternatives, and constraints, then evaluate alternatives, identify, resolve the risks. Then here you develop, verify the next level product, and then plan the next phase. So in the first quadrant, this is where you get to know the objectives of the system and the constraints. What limitations does it have? Then here you evaluate and you determine the alternatives that you have. What are you going to use? And then you evaluate the alternatives, which ones are suitable, which ones will not be used. You identify the risks that will be involved and you resolve the risks. Then in this phase you develop, this is where you develop the system, you verify if the system is okay before you go to the next level. Then the plan phase, here you plan in the next version or the next release what will we include. So it is a spiral. You can begin with the simple review of the objectives, then you do the analysis and you come up with the first prototype. Then here you have simulations, models, and benchmarks. So this is the concept of operation. This is where you start with the simple development and then you plan in the next phase, the next product, what should we include. So now here you continue. You go back and review the objectives of now the next phase and you analyze the risk. You have the second prototype, then you do the requirements. You can now do thorough validation, then you develop a plan to see if what should the next release incorporate. Then you determine the objectives in that for that release. You still do the analysis and you come up with the third prototype. So each release is like a prototype which you are using to gather the requirements and analyze it so that it helps you to come up with a better release, until finally when you continue in that spiral you will come up with the acceptance test, the integration, or you do all these tests, and now if the product is okay you deliver it to the user. But still, if it's not okay, you go through that spiral. So it's like each release or version is a prototype that is used to help you go back through all the phases as you further add the functionalities and further do the analysis. So that's the spiral model. I'm not going to explain that, I've been talking about them. Let's talk about the rational unified process. Now, a modern generic process derived from the work on the UML and associated process is the rational unified process. So this process, we are saying rational and unified. This process is the modern general process. We use UML notations and the processes that are associated with it. In this RUP, rational unified process, you bring together the aspects of all the other three general process models that you have discussed: the waterfall, the incremental, and the reuse based. So this is a rational, meaning it has looked at through all the advantages and disadvantages of each, and it will now focus on the advantages of each. Meaning if you combine, that's why you call it a unified process, you combine the processes from the other three perspectives, you have the strength of each as one in one process or in one model. So normally from the other three perspectives, we have a dynamic perspective that shows phases over time. We have a static perspective that shows process activities, and you have a practice perspective that suggests good practice. So this dynamic one is obtained from the incremental model, whereby the changes keep on coming and you keep on adding increments on each version. So it shows how phases do the change, they are dynamic. But again, it has the static perspective, whereby you can show the activities in each process as distinct activities. So you can know that I have to finish this and this and this. Then again, the proactive perspective, which suggests a good practice. From the reuse, you use already available components and to see that they work together to save development time, and you come up with a system. So this rational unified process has these phases: inception, and each phase is a cycle, is iterative within each phase. Then you have elaboration, construction, and transition. And again, the whole process as a whole is still in form of a loop. It is iterative. Then you go back in the process as a whole. So after transition, you can go back to inception, you do the elaboration, the construction, and then you do the transition. I'm going to explain each. Inception is where you establish the business case for the system. What does the business want? So it is the inception process where you're trying to understand what the system will be doing, what the user wants, and so on. As in, you are just grasping the concept, you are building it in your mind and to your team to understand it. That is the inception part or the phase. Then we have the elaboration. Now here you try to understand further the problem domain and the system architecture. What architecture are we going to use depending on the problem that we have? What problems the system solving or what functionalities in detail are required? So that's elaboration. You elaborate, you further try to get the understanding. Then construction. This involves the design of the system and then the programming and then all the testing, both unit testing and integration testing. Then transition. That's when you deploy the system into its operating environment, and still after transition you can go back and do the inception. You try to get maybe a wider picture of the system. Then let's talk about iteration. As I said, in each phase we have iteration. So each phase is iterative with the results that are developed incrementally. So first of all, we have phases. That is a feature. It has phases that look as if they are distinct. That's a feature of the waterfall. But in each phase we have iteration. So within each phase, like the elaboration, we can further understand and add more functionalities. Then you have cross-phase iteration. What does it mean? That's why it is shown by the loop here. This loop, we have cross-phase iteration, and this is in-phase iteration. So with cross-phase iteration, we are saying the whole set of phases may be enacted incrementally, as I've already explained. So we have static workflows in the rational unified process. These you will try to read and understand. Let's talk about the RUP good practice, the rational unified process good practice. Why is it having a good practice? We develop the software iteratively. You plan increments based on customer priorities and deliver highest priority increments first. So as you are developing, you look at what the customer wants first. You do it so that they start using it, and then you plan to add on other requirements. You do the increment. Then you manage requirements, explicitly document customer requirements, and keep track of changes to these requirements. Then use component-based architectures, organize the system architecture and set of reusable components. That's why I said this RUP will use the good features of all the other three general approaches. Okay. Then we have also visually model software. We use UML models. You learn UML models. If you don't know, UML is Unified Modeling Language. And with that language, you will be given with tools and notations to present static and dynamic views of the software to come up with good designs. Then you can verify the software quality. That is, you ensure that the software meets the organizational quality standards. You validate, then control the changes to software. You manage the changes using the configuration management tools, and you can manage the changes, or you can manage the changes, or handle the changes, or cope with the changes in the way that you've already seen. So lastly, these are the key points in the last part. We are saying that processes should include activities to cope with change, because in the real world, change is inevitable. So whichever process that you plan, make sure that you have room for change. And we are saying this may involve a prototyping phase that helps avoid poor decision on requirements and design. So as we have seen, you may use the prototype to help you do the right decision on which requirements and the design that is suitable. Then the process may be structured for iterative development and delivery so that changes may be made without disrupting the system as a whole. Yeah, we have talked about that. So it's better to use the incremental and or the iterative kind of development whereby you can go back and add the changes as they arise. And then we are saying the rational unified process, the RUP process, is the modern generic process that is organized into phases that you have talked about: inception, elaboration, construction, and transition. But it separates activities, requirements, analysis, and design from these phases. Okay, so these activities can be all included within each of the phases. Okay, my friends, thank you for watching this video. I request that you subscribe to my channel. God bless you.